Okay, now we're going to talk about aqueous solutions in which you have water as a solvent. We're going to talk about ionic compounds in those solutions. So most solutions that you deal with are aqueous solutions. Water is the universal solvent. So coffee, tea, Coke, vinegar, all of these have water as the solvent. In aqueous solutions, there are four driving forces. And one of them is the formation of a solid, the formation of water, transfer of electrons, and the formation of a gas. So we're going to focus a lot on these two, touch upon this and not really get into this, but we'll talk about this later in the course. A reaction in which a solid forms is called a precipitation reaction. A solid is a precipitate, and so when you mix two solutions together that are aqueous, that are fully dissolved, and a solid forms, that's what's happening here. You can see it turning cloudy because its solid is forming. We call this, in chemistry, we call this a precipitate. So it's a precipitation reaction. When ionic compounds are able to dissolve in water, they break up into their individual ions. So this is what the term aqueous means. Aqueous means that this ionic compound, it no longer exists as this unit anymore. Instead, it exists as these ions that are surrounded by water molecules. So we have chlorine surrounded by water molecules, sodium surrounded by water molecules. And so we no longer have this substance as a solid. We've got it dissolved in water. Individual ions are broken up and surrounded by water molecules. Here's another picture of sodium chloride. You put it in water. Once it all dissolves, you've got it breaking up from its salt form, in which it's like a crystal structure, and then being surrounded by these water molecules there. Sometimes when you have aqueous solutions of ionic compounds and they mix, an insoluble compound or precipitate is formed. That means that it is not surrounded by water molecules. It falls out of the solution, kind of like here you have this at the bottom of the solution. Sodium chloride will eventually dissolve, but some of them won't. It won't ever dissolve. And so it falls out of the solution as a solid. So it's no longer surrounded by water molecules in the solution. And so, for example, if we have ammonium sulfide and cadmium nitrate, when you put those in water, you have two aqueous solutions. You've got these ions surrounded by water molecules in the solution. When you mix them together, though, a precipitate will fall out, because what happens is the cadmium sees the sulfide, and when these react together, they form a precipitate. It's not soluble in water. Water is not surrounding it as individual ions. It falls out of the solution as a solid. So that is the driving force of this reaction, the formation of cadmium sulfide. You still have these ions floating around in the solution, but the cadmium and the sulfur have, or the cadmium sulfide has fallen out as a precipitate. So here's a picture of what this looks like before the reaction. You've got sulfide, you've got ammonium surrounded by water molecules. Solutions here of cadmium and nitrate. Each of the ions are surrounded by water molecules. When you mix it together, though, cadmium sees the sulfide and it ends up forming this crystal structure that water is not able to penetrate. And so water is not able to break these ions apart, and so it falls out of solution as a solid precipitate. So when we represent these reactions, ions, we say that ions that don't take part in the chemical reaction are found in solution before and after are just spectator ions. They exist before and after as aqueous ions. And so in this case, the nitrate and the ammonium end up as nitrate and ammonium. So they're kind of like in algebra where you have the same thing on each side. You cancel them out. These are just spectators. What's actually taking place in this reaction is that cadmium is finding sulfide and forming this solid. And so that is the net equation or net reaction that's actually happening. And so we have a way of representing that to cut out the spectator ions and just show what's reacting. So the net ionic equation would be only the compounds and ions that undergo a chemical change. So what's really happening in that solution is that cadmium sees sulfide. These form an insoluble solid that falls out of the equation. It's a precipitate. Sometimes we show it like this with a down arrow because it's falling out as a solid in that solution. So here's how you would get there. You'd start with this reaction, and then you're going to write this complete ionic equation. And what happens there is anything that's aqueous, you're going to break that apart because that's what it does in water. If it's solid, here, solid, you keep it together. So here, we also want to make sure that is balanced, which I believe it is. The key here is when you're breaking up these ions, you want to make sure that you're representing how many of each ones there are. And so these subscripts for the ions are going to become coefficients. But you never want to break up polyatomic ions. And so never break up the polyatomic ions. Atomic. So you want to keep them as a unit. So I want to keep NO3 as a unit, NH4 as a unit. But those subscripts tell me how many of them I have. And so I'm going to put, I've got 2 NO3s and I've got 2 NH4s. I've got 1 sulfide, I've got 1 cadmium. Here, cadmium sulfide, keep that together. And then, wait, it looks like this actually was not balanced. I think we just need the 2 there. Okay, and so we've got 2 NO3 and 2 NH4. Once you do that, you can cancel out spectator ions. So I've got these on both sides, these on both sides. And so this is my net ionic equation. These ions are what's left because they form the solid. Here's another example. You've got potassium chromate reacting with barium nitrate to form barium chromate, which is a solid, and potassium nitrate. So we're going to break apart everything. So see how you've got 2 potassium ions. We have to know the charges here because when it breaks into ions, it's got a charge. So potassium, chromate, barium, we've got 2 nitrates. That forms barium chromate, which is a solid, so we don't break it up. Potassium and nitrate, 2 of those. These cancel. And this is your net ionic equation. So here is an example. We've got aqueous cobalt 2 chloride. So here's our molecular equation. Cobalt 2 chloride is aqueous. It reacts with aqueous sodium hydroxide. So you've got 2 aqueous solutions. These exist as ions floating around in solutions surrounded by water molecules. When you mix them together, though, we form aqueous sodium chloride and solid cobalt 2 hydroxide. So that's the driving force of this reaction, the formation of this solid right there. Then I'm going to balance it. So I want 2 chlorines and 2 hydroxides. So it looks like that is now balanced. Okay, so now I'm going to break up everything that's aqueous, leave together that solid. So I've got a cobalt ion that's a +2 charge and aqueous. I've got 2 chloride ions that are aqueous. So they don't exist as Cl2, they exist as 2 Cl- in solution. I've got 2 sodium ions and I've got 2 hydroxide ions. That's aqueous. That's aqueous. So this is what this reaction looks like before. You've got all these ions floating in solution. When you get over here, though, when they meet each other, cobalt sees the hydroxide and forms a solid. But you've still got this aqueous sodium chloride in the solution. So you've got 2Na plus still floating around in water as ions. But this, the cobalt and hydroxide have found each other and formed an insoluble precipitate. So now we can cancel out what's on both sides. We've got this, sodiums, and 2 chlorides. And so the net ionic equation is cobalt plus 2 hydroxides. That forms cobalt hydroxide solid. And that is your net ionic equation. Okay. Another type of these reactions, these aqueous solutions, are when you have acids and bases react with each other. So we're going to talk a little bit about acids because we haven't talked about that before. We'll talk about this later in the next semester. But we're just going to briefly introduce this. So acids are a molecule with 1 or more H plus ions attached to an anion. And so here on the periodic table, hydrogen's in this group of the +1 ions. And so hydrogen also can form these ions. And when it does, it's called an acid. And so most acid formulas begin with H, and here are some examples of them. When they dissolve in water, just like ionic compounds, they dissolve into their respective ions. So you've got a hydrogen ion, Cl-. This right here is what makes things acidic. It's what makes things taste sour, like vinegar or lemon juice. It's the hydrogen attached to a water molecule that makes it taste like that. Binary acids contain 2 different elements, and so that's when you have hydrogen reacting with any of these here or sulfur. But also hydrogens with water, but that's not really an acid because it is effectively a neutral substance, which we'll also talk about later. But any of these, here you can see these substances there and their names, which we'll have in another slide. You basically start with hydro, end with ic, and acid. And so when you have this, the name of the binary acid begins with hydro. Then you put whatever this is, the root of that, in there. So if it's chlorine, it's chlor, fluorine, fluor. And then you end it with ic, acid. Oxyacids are basically hydrogen attached to a polyatomic ion in the number of whatever the charge is. So PO4 is a -3, sulfate is a -2, and so here you have 3 hydrogens, here you have 2 hydrogens to balance that out. And the way we name these is if the polyatomic ion ends in 8, change it to ic. So HNO3 would be nitric acid, H2SO4 would be sulfuric acid, because this is nitrate, this is sulfate. Notice that they add the uric, the ur back in to make it sulfate, so that's just a weird thing that they do. Polyatomic ion ends with ite, change it to us. So HNO2, this is nitrite. And so it's nitrous acid. This is sulfite, sulfurous acid. And here are the reminders of that. And so look over that We won't do a lot on that now, but I just want you to know how that happens and how these are named and what an acid is. When strong acids and strong bases react together, which a strong base is basically anything where you have hydroxide minus react together, it always forms a salt and water, where the salt is an ionic compound contained from a cation of a base and an anion of an acid. So for example, HCl, NaOH. And so here a base is something that contains hydroxide and a metal cation. It forms a salt here and then water, because basically what you're getting here is H plus and OH minus that come together to form water. And this water is a liquid, and that's the driving force of this reaction. So what I mean by that is that here, if you've got these reacting together, everything's aqueous except for the water that's formed. So we're going to break this up for the complete ionic equation. You've got aqueous hydrogen ions, aqueous chloride ions, aqueous sodium ions, aqueous hydroxide ions. When you mix that together, you've got aqueous sodium again, aqueous chloride, but then liquid water is what you're forming. Those aren't ions anymore. When the H sees the OH minus, it forms water. So then we can cancel spectator ions. We've got H plus OH minus forms H2O liquid. Any acid-base reaction that contains this hydrogen and then the OH, it's going to be the same type of reaction, and that ionic equation is always this right here. So for example, the net ionic equation for the reaction of HNO3 and LiOH, it's this guy seeing that guy to form water. That's the net ionic equation. So those are all incorrect. This is going to be the answer for any strong acid and strong base. Okay. Briefly, we're going to talk about this. You can get really in depth with oxidation reduction. I'm just going to briefly talk about what that is. This is when you have a transfer of electrons in a reaction. Oxidation is the loss of electrons. Loss of electrons means something's getting more positive. So either getting positive or getting more positive. Gain of electrons means getting more negative because you're gaining electrons. So for example, if you have sodium and chlorine coming together to form sodium and chlorine ions here, you've got sodium losing an electron. So here you've got 11 electrons versus 10 electrons to give that positive 1 plus charge. Chlorine has 17 electrons, goes to 18 electrons to get the minus 1 charge. And so here it's sodium that's being oxidized, and you've got chlorine that is being reduced. Reaction between metals and nonmetals involve a transfer of electrons from the metal to a nonmetal. So here when you have magnesium and oxygen, this oxygen, usually when that's reacted, it means that you're burning something. And so when you burn magnesium, you end up with this substance here. When they're in their elemental forms like this, their charge is 0. They don't have any charge because they're neutral. And so you've got neutral magnesium and neutral oxygen. And then over here, you've got magnesium as a +2 and oxygen as a -2. And so then what's happening is oxygen is stealing electrons from magnesium, or magnesium's giving electrons to oxygen. And so magnesium here is becoming oxidized. Oxygen is being reduced. There. More positive, more negative. It's all about this transfer of electrons. Another example, when you've got these two coming together, cesium and fluorine, it's 0, 0, but that ends up being +1 and -1. And so cesium is giving up an electron. It's losing an electron. It's being oxidized. And fluorine here is being reduced because it's gaining an electron. Here on this side of the equation it means it's losing it, it's being produced. Here it's kind of reacting with that to form F-. Another type of oxidation reaction is when metals replace other metals in compounds, resulting in transfer electrons from the elemental metal to the metal ion. So for example, if we've got aluminum here that's a 0 charge, it's neutral. We react with iron oxide. Here, iron's got a +3, oxygen's -2. On the opposite side here, you've got neutral iron. Aluminum now has a +3, oxygen's still -2, so nothing's really happening with oxygen. But aluminum is giving its electrons to iron. So iron is taking these electrons from aluminum. Now aluminum is in the compound with a positive charge. Iron is now neutral. So electrons are transferred from aluminum to iron. And so that means that aluminum here is being oxidized. Iron is being reduced. So for each of the following reactions, show how electrons are gained and lost. Here you've got iron with a 0 charge, oxygen with a 0 charge, and because elemental oxygen always exists as O2, and so that's why there's that 2 there. Over here we've got iron as a +2 and oxygen as a -2, and therefore iron is losing electrons. It's being oxidized. Oxygen is gaining electrons. It's being reduced. Here we've got aluminum. It's a 0 charge there. Lead here with nitrate is +2. Nothing's happening with nitrate, so I'm going to ignore that. But I end up with here the lead has 0. Aluminum is now +3. And so aluminum is becoming more positive because it's losing electrons, giving its electrons to the lead, which is now 0. So aluminum is losing electrons. It's being oxidized. Lead gaining electrons. So it's being reduced. Goes from +2 to 0. This one goes from 0 to +3. So essentially aluminum's losing 3 electrons, lead's gaining 2. And then you have the coefficients to balance that to make sure there's an even number of electrons and atoms on each side of the equation. Okay, so we're not doing any more in-depth problems than that. I just want you to be able to identify what is being oxidized and what is being reduced in these reactions. And that is it. So go and do the practice worksheet for net ionic equations, and then you can go ahead and take your quiz.